Okay, so this is sort of opposite. A solid cylinder rolls up incline of angle 20 degrees. If it starts at the bottom with a speed of 10 meters per second, how far up the incline does it travel? Okay, so now this is sort of the opposite problem. So they give you it's a solid cylinder. When they tell you it's a solid cylinder, what they're telling you is they're giving you its moment of inertia. Its moment of inertia is 1/2 mr squared, the same as that of a disk. Okay, and the incline is 20 degrees. Okay, so now you can calculate the acceleration of. Okay, so the acceleration of this guy in that direction again is g sine theta minus 1 plus I center of mass divided by mr squared. Well, since they told you what the object was, you knew this guy in terms of that. This ratio is 1/2. Okay, so okay, what does that mean? What does this mean? So if you shoot an ice cube up the incline, its acceleration would be, its deceleration would be g sine theta. As this thing rolls up, its acceleration is 2/3 g sine theta. It rolls further. Very good. Okay. So that's what that means. Okay. So now we have the acceleration. Okay. So again, what will be your? This will be your x-axis. What is it? How far up the incline? So what we could do is we could use this formula: v square equal to v naught square plus 2ax minus x naught. Why are we using this? Do you know the final velocity of the center of mass? 0. Very good. Okay. That's 0. What is this? 10. This is what we're finding. Do you know this? Yeah, you can calculate that. Okay. All right. So let's. By the way, our acceleration will be negative because this is the positive direction. I just calculated the magnitude. The acceleration, deceleration, it's a deceleration. It's pointing in that direction, okay? So this is equal to 0 minus 10 square meter square second square divided by 2 times minus 2.23 meters per second square. Okay, so 1 meter will be left. Okay, and so this is equal to Okay, so this cylinder, 10 meters per second, that's how fast Usain Bolt runs. Okay, that's 25 miles an hour. So if you take this cylinder, send it at 25 miles an hour, it'll go from here to there. Yeah, that's what that is. Yeah. All right, so in this problem, a Formula One race car with a mass of 750 kgs. That's a light car. I drive a Honda Civic and that weighs 1500 kgs. What's that? Yeah. Well, and then it's got to have a lot of foo-foo stuff. Formula One doesn't have to have foo-foo stuff. Yep. Airbags are heavy?
Well, no, you've got airbags, air conditioning.
Yep. All right, so speeding through a course in Monaco, enters a circular turn at 220 kilometers per hour in the counterclockwise direction about the origin of the circle. At another part of the course, the car enters a circular turn at 180 kilometers per hour, also in the counterclockwise direction. If the radius of curvature of the first turn is 130 meters per second, 130 meters and 100 meters, compare the angular momentum. All right, so we have to turn these speeds into meters per second. Okay, so 220 kilometer, what is the prefix K? So the prefix K is 10 to the power 3, okay? And 1 hour is 3,600 seconds, okay? So to convert it to kilometers per hour to meters per second, all you have to do is divide by 3.6. Okay. So this is and then also, so the velocity on the second turn is 180 kilometers per hour, and divide that by 3.6. That's 50 meters per second. All right, so you guys saw that angular momentum when you're going on a circular path. Angular momentum is given by mvr. Okay, so angular momentum is the mass of the car is 750 kgs. I'll just do it for one thing. 61 plus 0.1 meters per second, and r is 130 meters. Okay, so the units will be kg meter square per second, okay? And this is one of the places where this combination of units doesn't have a name. Okay, that's the angular momentum, and you can do the same thing for the other thing. Okay, now I'll calculate something that the problem doesn't ask. So let's calculate the centripetal acceleration. Turn 1. is V squared by R. Okay, in Formula One racing, the tracks are all flat, right? The road is all flat. In our 24 hours too, we do in the infield and all the roads are flat. So what is providing the force for the centripetal for when you make a turn? Static friction. Okay, so your track, cars, your tires had better be sticky. Okay, so this is 61.1 squared divided by 130 meters. So the centripetal acceleration in turn 1 is 28.7. Look at that, 2.93 Gs. Absolutely amazing. The car's tires are sticky enough to hold on to the road with 3 times the weight of the car. All right, let's do turn 2. You guys understanding that? What's that?
Stick to the wall, right?
Looks like it. That's crazy. Okay, so let's do the other one. What is the speed? 50 meters per second. .55 Gs. So you made the second turn slower. Well, you could have made the second turn faster because your tires were sticky enough. So you left money on the table. What happened? It's a tighter turn. It's probably getting crowded, not enough space. That's it.
We don't know what's after the turn.
What's that?
We don't know what's after the turn.
No. Well, it's probably safety is the only thing that because they live on the edge. So if they could have gone faster, they would have gone faster. No, that's all I'm guessing. But those were interesting numbers. That's yeah. Yep.
For the question, the angular momentum, you only had to find one of the terms?
No, you had to find the other one too, but it's boring. The second number was much more interesting. And this number, what does this number mean to you? Nothing. Right? So, yep.
So that number,
Mhm.
is saying it requires that many kilograms per square meter per second to stick to the track?
Mm,
You don't want to be in front of that car once going to the turn.
So this is where stuff comes. Okay, I don't have a clean answer to the question, so I'm just. To me, the second one was okay. So here's where it comes in. Okay, when you calculate angular momentum, if you want to stop it, okay. So when we were doing linear momentum, we had linear momentum for If you look up tables, linear momentum for a baseball and linear momentum for a rhinoceros and a car and stuff like that. That's relevant because that'll tell you what kind of force you need to stop the object. Okay. So here, parallel would be what kind of torques would you need to reduce that angular momentum. Okay. So for instance, if you have a motor spinning, if a wheel is spinning, you calculate its angular momentum, and you want to stop the motor in, let's say, 10 seconds, what kind of torque would you need? Yeah. Yep.
Where is the torque applied on like a F1 car?
Well, you would, so the braking torque,
Semi tire.
yeah, I mean, it's, you don't have the Formula One on a string that somebody is whirling. Yeah, you know? The only thing under your control is the brakes. Yeah, so anyway, what I want you guys to do is think on what the problems mean, okay? Sometimes just, all right. So this problem says, at a particular instance, a 1 kg particle's position is given by that. So this is with reference to some coordinate system, okay? Its velocity is that, and the force on it is that. What is the angular momentum of the particle about the origin? So you're calculating angular momentum and torque and everything about the origin. And if you guys look at your definition, L is equal to R cross P, okay, which is M times R cross V. Okay. So this problem is about finding cross products. Okay. And so let me remind you of the cross products. I cross J is K, J cross K is I, K cross I is J. And if you go in the opposite direction, what is I cross K?
J.
Minus J. So it's in the, okay. So the way to remember this is the following. The best way to remember this is I, J, K. Okay, so you turn a screw from the first vector, so I cross J. So whatever is the first vector, you're turning from that vector to the second vector. If you turn a screw this way, which way will the screw move? That way, okay? And that's the direction of the cross product. So the cross product is perpendicular to the plane containing these two guys. And you just have to decide, is it in that direction or that direction, okay? And to help with that, so sometimes you won't be able to do this, but this is also useful, okay? This is the first vector, second vector, and that's the direction of the cross product, okay? Anyway, so since you're given I, J, and K, this is a useful one to remember. So I will, so this is 1 kg, mass is 1 kg, R is 2I minus 4J plus 6K crossed with minus I plus 4J plus K. And the units will be, what are the units for angular momentum? Mass is kilograms. That is meters per second, that's meters. So kilograms, meter square per second. Okay. All right, now let's calculate the cross products. I cross I is what? What is I cross I? I'm sorry? Any vector crossed with itself is 0. Okay? A cross A is 0. Okay? And how do you remember that? The magnitude of A cross B, the, again, all these formula are in your notes. The magnitude of A cross B is, anybody remember that? Is magnitude of A times magnitude of B times sine theta. And for A cross A, theta is 0, sine 0 is 0. And if vectors were anti-parallel to each other, theta would be 180 degrees, sine 180 is also 0, okay? So the cross product of parallel and anti-parallel vectors are 0, okay? Anyway, with enough practice, you'll remember all of that, okay? Okay, so I cross I is 0. I cross J is K, okay? So this would be 8K. Then I cross K is what? I'm sorry? Yep, I cross K is negative J, so minus 2J. Okay, that took care of that. Now let's do this. J cross I is negative K. There was a negative, negative, and then you get a negative. So negative 4K. Then what is J cross J? 0. What is J cross K? I. So that's minus 4I. Okay, and then K cross I, J. So that's minus 6J. K cross J, minus I. So that's minus 24I. And K cross K is 0. Okay. So now you just add them up. Okay, so minus 28I and minus 8J plus 4K. Okay, so that is the angular momentum. That's the angular momentum about the origin. You can calculate the angular momentum about any point you want. Okay, so depending on what point you calculate it about, you'll get different values. As you calculate about different points, this will change. Okay, the velocity doesn't change. It's okay. Torque is given by R cross F. So we're going to calculate the torque about the same point. 2I minus 4J plus 6K. And units are, what are the units? Newton meters. Okay, so here's something you want to remember. Newton meter in a different context is this combination is named joules when you refer to energy. Okay, when you're referring to torques, you keep it as Newton meters. Okay. And in BTU, British thermal units, as our friend said, it's foot-pounds. Okay, that's what your car, the torque on your car is listed as. Okay. Okay, so I cross I is 0, I cross J is K, so that's 30K. And J cross I is minus K, so that's plus 40K. And then J cross J is 0. K cross I is J. K cross J is minus I, so minus 90I. Okay. So that's part B. And C was what is the time rate of change of the particle's angular momentum at this instant? Okay, torque is equal to dl by dt. Okay, so the rate of change of angular momentum, the rate at which this guy is going to change, is equal to that. Okay, so that's what that is. Okay, this problem says a boulder of mass 20 kgs and radius 20 centimeters rolls down a hill 15-meter high from rest. What is its angular momentum when it's halfway down the hill at the bottom? Okay, so it's 15 meters high, and so we're going to assume it's a spherical boulder and it's rolling down. Okay, so halfway, so this would be 7.5 meters. Okay, so we can solve it two different ways. Well, so what I'll do is I'll just solve it using energy conservation. Okay, so mechanical energy is conserved. So what is happening at this point? What do you have? Gravitational potential energy. At this point, we'll assume this is the zero level for gravitational potential energy. So you have all the gravitational potential energy has been converted to what kind of kinetic energy?
Gravitation.
It's rolling, so it's spinning and translational. Okay, so it'll be rotational and translational kinetic energy. Okay, so initial equal to final. mgh equal to 1/2 I center of mass omega square plus 1/2 m times v center of mass square. So this is rotational kinetic energy, and this is translational kinetic energy. And if it's rolling without slipping, then this guy is related to that guy. Okay, v is related to, okay, so v center of mass is r, the radius, times omega. Okay, so we can write, okay, and you can look up for a boulder, it's 2/5 mr squared. Okay, so for a solid sphere, it's that. Okay, so let's write this. All right, let's make sure of that. That's sort of. You can Google moments of inertia. Moments of inertia. Yep, for a sphere, it's 2/5 mr squared. Okay, so mgh equal to 1/2 into 2/5. V is r omega, so All right. They want us to find the angular momentum. That's fine. Okay, so you see this is V. That's V. Okay, the mass will cancel. What does that mean?
Constant.
What's that?
Mass is constant.
No, it's not constant. No matter how heavy the boulder, they all will be going at the same speed. It's like if you get on a ski slope and you're skiing down, your mass doesn't matter. As long as you're wearing the same kind of skis, you'll be going at the same speed. You know. So the mass cancels. Okay, let me copy this and. Okay, R omega is V center of mass, so this is V center of mass square plus 1/2. Okay, so the boulder rolls down 7.5 meters, so we can calculate the center of mass velocity. Okay, and 1/5 plus 1/2 is 10 2 plus 5, 7/10. So what is H?
So it's 1.5.
Mm-hmm. Okay. What they ask you to calculate is what is the angular momentum of it halfway down the hill. Angular momentum is, so I times omega. I is 2/5 mr square. Omega is V over R. It's 2/5 mRV. We know the mass of the boulder, we know the radius of the boulder, we calculated the V. Okay, so you can plug that in. So here, this is interesting. Okay, so for so you guys saw that for a planet point particle going at the angular momentum is mvr. So for this boulder rolling down, it's mvr. It's mvr, 2/5 of that. Okay. Anyway.